All right, well, I think we can get started. Again, welcome everyone to our seminar series. Great to see some familiar faces and some new ones as well. We're lucky here to have with us again Bryan Wilder, Dr. Bryan Wilder from Machine Learning Department, where he's an assistant professor here at CMU. His research focuses on AI for equitable, data-driven decision-making in high-stakes social settings, so very relevant to AI-SDM. He's also involved with integrating methods from machine learning, optimization, and causal inference. And here at CMU, he directs the Lab for AI and Social Impact. So looking forward to his talk here today. The floor is yours, Bryan.
Thanks, Norm. And yeah, thanks everyone for being here. So today I'm going to talk about predictive versus causal targeting of social interventions. And so I want to start out by breaking down what I mean basically by all of the words in this sentence. So to start out with targeting, which is really the focus of this talk. So targeting is the question of deciding which people should be offered a treatment or an intervention that is in some way limited, right? So the need to target is induced by the fact that we can't or shouldn't, sort of give some sort of intervention to everyone who might be eligible for it. And so we want to figure out who kind of the best candidates are. And so this kind of idea is fairly ubiquitous across a wide range of important application domains, right? So for example, in a development context, different organizations might want to figure out how to target a cash transfer, right, or another sort of economic intervention. In human services, right here in Allegheny County, right, the government has to decide how to prioritize people for access to housing assistance, either kind of preemptively when people are in danger of being evicted or after they actually become homeless. Or in medicine, we think a lot about preventative screening, right? So we're not going to, for example, test everyone for diabetes all the time, or that would be ridiculous, but we might sort of identify people that we think are particularly good candidates for screening because it will improve their health. So when we try to figure out what the right targeting strategy is, I think there's a substantial gap between the way that people think about this kind of in the academic literature, which I'll call theory here, and what usually happens in practice. So in theory, the kind of go-to answer is that you should estimate what are called heterogeneous treatment effects. So this is basically a quantity that describes as a function of some observable covariates of a person, what the benefit that they will realize is from getting the intervention, right? So if I offer this person a cash transfer, how much will that improve their economic circumstances in a year or whatever time horizon? And so this is crucially a notion about counterfactual outcomes, right, and benefit from intervention. It's asking what will change about the world if I offer this person an intervention. And so across different technical literatures in computer science and economics and statistics and operations research, this kind of gets called different things. And so I have some of the kind of the phrases that you might be familiar with here, but these concepts are all kind of referring to the same, I think, essential strategy. On the other hand, in practice, this almost never happens. So what happens in practice is that people estimate risk scores. And so a risk score is not reasoning about a counterfactual world. It's not reasoning about what will change if I give you an intervention. It's reasoning about what will just happen right now if I don't do anything. So in the status quo, what is the risk level of this individual? And the reason for that is that fundamentally learning about causal effects is hard, right? We need data that allows us to draw that contrast in outcomes, which requires that data be gathered in very particular ways, right? So most prominently, we would conduct a randomized controlled trial where we would actually assign people to intervention or not, and that would allow us to draw strong causal claims. But for various reasons, that doesn't usually happen. Doing this estimation is really hard. And so there's very few examples of anything in this category actually kind of like making it to the real world in any of these domains. And so as a result of that, perhaps, risk scores are basically everywhere, right? So there's countless examples in any number of domains. Again, these get called different things maybe in different settings. But a lot of the kind of the most prominent sort of way that these decisions are made in practice right now is basically by fitting models to predict risk in various forms. And so this is kind of speculation on my part, but I would guess that these sort of risk assessments are really the most common class of algorithms that impact people right now in high stakes settings, right? They're sort of absolutely ubiquitous. And so this talk is covering a couple pieces of work that try to answer two related questions around this sort of tension between predictive targeting, right, risk scores, and causal targeting. So the first piece of work tries to ask, is predictive targeting enough, right? If this is what everyone is doing right now, is this actually sort of a reasonable strategy? And so we have a first empirical piece of work trying to answer that question. And then second, to the extent that it's not, how can we bridge the gap, right? How do we move from predictive targeting towards more causally informed targeting in a way that's kind of feasible given the constraints of these application domains? So I'm going to start out with this first piece of work. So this is a recent work. The preprint, I think, is up or should be up in a day or two, led by Vibhu Sharma, who's a master's student here at CMU. So when we ask, is predictive targeting enough, or is predictive targeting good? The challenge is that there's actually very little empirical evidence available. So there's a small handful of studies that have tried to look at this question in individual domains, right? So for example, this paper by Susan Athey and Jan Smees and co-authors tries to examine a particular, intervention around texting students to get them to renew their financial aid application. But really, we have these sort of, fairly sort of narrow individual viewpoints. And part of the difficulty in doing this is that if I want to contrast predictive and causal targeting strategies, I need to be able to actually make inferences about treatment effects. And in most observational settings, this is really difficult. We worry that treatment assignments are in fact confounded, or there's selection bias, or kind of other things that will lead us not to be able to draw causal conclusions from the observed data. So in this work, we use data from 5 different domains where a randomized controlled trial was actually conducted and where there was substantial covariate information available that allows us to make inferences about heterogeneous treatment effects. And so this spans a wide range of applied settings, including development economics, education, medicine, and kind of labor interventions in the US. And because we have access to the randomized data from the trial, we can estimate something that's at least much closer to a ground truth treatment effect, right? The treatment effects are in principle identifiable in the data that we have. And this allows us to compare causal and predictive targeting. So the first question that I'm going to sort of show en route to try to answer this is just, do treatment effects actually correlate with predicted risk, right? Are people who are at greater risk of adverse outcomes also people who benefit more from receiving an intervention? And this is not necessarily obvious, right? Like you can imagine that in many domains, people that have very high levels of risk, it's also hard to move outcomes for them, for example. So
Bryan, can I ask a clarifying question quickly?
Yeah, go ahead, Archie.
So when you say predictive targeting, you mean just who's predicted to be most at risk, not who's predicted to benefit the most, right?
Yeah.
Yep. Okay. Thanks.
So here's a set of plots that are trying to answer that kind of initial question. So the x-axis of each of these plots is what percentile an individual falls in the baseline distribution of predicted risk, right? So this is if we don't do anything, how bad do we think their outcome is going to be? Or 100 is, the 100th percentile is the worst and 0 is the best. And then the y-axis here is the estimated conditional average treatment effect given that level of risk. And so the thing that there's basically a few things I want to point out about these plots. The first is that they are generally kind of increasing, right? So it is the case that across most of these domains, if you compare low levels of risk to high levels of risk, the estimated treatment effects do tend to go up, right? So this is at least a kind of like basic validation of maybe the idea behind risk-based targeting, that on average, yes, people at higher risk do tend to benefit more from intervention. The second thing, though, is that this relationship is really like wildly variable across these domains, so even with that kind of general message. So for example, as one specific instantiation of that, if I try to mark the point on this plot where it seems like benefits kind of level off basically as a function of risk, you can get basically any point on the x-axis across these domains, right? So you really have no idea where basically individuals start to benefit the most from intervention. So to summarize what we have so far, it seems like on the one hand, the intuition behind risk-based targeting that seems to be shared by practitioners in a very wide array of domains is not completely crazy, right? Like high-risk people do on average benefit more from intervention in our sample here. But the sort of the nonlinearity in that relationship is really domain dependent. And so now we can ask, how does targeting based on estimated risk compare to targeting based on estimated treatment effects? And we can ask that both when we were able to estimate the treatment effects kind of correctly in principle, and when those treatment effects have some amount of bias. Because this is really the kind of the concern in practice, is that I don't have the randomized controlled trial. The effect estimates that I get might be biased by some residual confounding in the data. And so what we can do is synthetically inject some level of confounding basically into the randomized data that we have to kind of mimic that setting. So I'm going to pull just one plot out here that's kind of representative in some way. There's a lot of plots in the paper if you're curious. But this is the kind of the general story. So here, the x-axis is the amount of confounding that we synthetically add to the data, right? So more of this means that the algorithm's job has gotten harder, right? It's learning something that's not the true treatment effect. And then the y-axis is aggregate utility, which is measured as the basically average change in outcomes among people who receive the intervention. So this is a kind of like utilitarian welfare. And so what we find is that when we're able to learn treatment effects exactly, then targeting based on treatment effects is way better than targeting based on risk score, which is in turn better than sort of uninformed targeting, right, random. So this matches up that, yes, we're getting some benefit out of risk scoring, but there's a lot that we're leaving on the table, right? If we could learn the true treatment effects, we could in principle do a lot better. And now as we add more and more confounding to the data, I realize that the units on the x-axis here don't mean anything without more context. But you can think of this basically as this extreme is like very severe adverse selection into treatment. So basically this corresponds to that we're throwing away 40% of the samples in the data set in a way that creates a lot of selection bias. So this is a relatively severe level of confounding, I would think. And by the time we start to get there, then any benefit that we're getting out of learning treatment effects has kind of vanished basically because we're unable to do a good job. So there's relatively similar conclusions, that we get across a wide variety of data sets. While the plots look a little bit different, this is the kind of essential takeaway. A final analysis that we do here is to ask about preferences for equity, right? So maybe decision makers sort of know all this, but they have egalitarian preferences. They place greater weight on assisting people who are worse off right now, right? Because the sort of the utility function that I showed here on the left plot, I said was a utilitarian kind of welfare, right? So it weights everyone equally and just asks to improve outcomes as much as possible on average over the entire population. But maybe that's not what policymakers want to do. They specifically care about people who are in worse shape right now and helping them out. And so quantitatively, we kind of instantiate this by measuring welfare with respect to a couple of alternative utility functions. One is still a utilitarian style welfare, but where we include welfare weights on different individuals. So some individuals count more towards the objective than others. And those weights scale with predicted risk. So people get bigger weight if they're in worse shape, i.e. have higher levels of risk at the moment. And then the other is a Nash social welfare, which you can think of as basically evaluating utility on the log scale so that you get diminishing returns to having a lot of utility, right? Like we don't care if people have a lot of income just as if they move from low income to a little bit, for example. So here, I'm just going to quote kind of like one representative result. Again, there's lots of tables and figures in the paper. That in order for us to rationalize risk-based targeting, right? So for us to get to kind of that break-even point where according to our utility function, targeting based on risk would be as good as on treatment effects, we would have to weight people who are at high risk much, much more than people who are at lower risk. So as a kind of quantitative figure to anchor on here, when you compare someone at the 75th percentile of the risk distribution to someone at the 25th percentile, you would have to care about the person at the 75th percentile about 7 times more. So this, I don't want to say this is impossible, but it seems like at the very least we would have to have a lot of heterogeneity in how much we care about helping different people, basically, in order to sort of fully rationalize risk-based targeting. So to kind of sum up so far, it seems like risk-based targeting does have a real motivation, right? So it captures something about heterogeneous benefit. It's potentially motivated by equity concerns. And very importantly, it's easily implemented using kind of existing data, but it's difficult to kind of rationalize it as really the optimal thing that we ought to be doing. It seems like kind of under a wide range of possible preferences that a decision maker could have, there's room to do something better. So now I'm going to switch gears and talk about basically then how do we bridge the gap to improving targeting strategies. But I'll pause here if people have more questions about this first piece.
Yeah, I guess, so when you talk about like risk algorithms, so I would imagine, first of all, you have a set of covariates X, for example, and then like a risk, some function on that X. And then, the heterogeneous treatment effect is some like other kind of functional on the same kind of X. So at one point, like, I guess one thing is that obviously risk algorithms tend to be parametric models and then, but like when you try to learn treatment effects, you try to like avoid that kind of assumption, like at what point does it converge? Is there a point that we are safe to say there is like some parametric structure or like lower dimensional representation of the treatment effect such that the risk like is much more correlated with the heterogeneous treatment effect?
Yeah, this is an interesting question. I think to some extent, these are kind of different axes, right? So like one is, what is the model trying to estimate, right? Is it like the baseline outcome or is it the difference in counterfactual outcomes? And the other axis is how complex is the model of those outcomes. And so I think you're correct that practitioners typically use fairly simple, parametric models right now. From a research perspective, I think this has just changed over time, right? Like people used to use kind of simpler parametric models to reason about treatment effects. Now there's more kind of interest in non-parametric methods because we have like kind of better statistical tools and on average larger data sets. But it still may be a very application specific question about which you prefer. So I don't think parametric versus not is somehow like the fundamental distinction between the two strategies. As to the question of whether if we basically, it sounded like you were asking like if we had the right representation somehow, if the two kind of notions would kind of like coincide more, basically. Yeah, this is also interesting. I think we should expect that they, like, it seems unlikely that they would like fully coincide. You know, for example, even if you like were able to really optimally like learn the optimal non-parametric model for each quantity, it does seem just kind of like, I don't know, intuitively, like in terms of, I don't know, our own just understanding of the world, we should think that, they're not always the same, right? Like people might benefit, like even people at the same level of risk might benefit different amounts from a given treatment because of like different mechanisms, for example, that would explain why they're at that risk level. So that seems likely. I think there is some interest in whether you can capture treatment effects as kind of like a low dimensional like correction basically to risk, for example. It is an empirical question. Yeah.
What's the impact of kind of the number of parameters that you're measuring to your choice of your belief in the effectiveness?
Yeah, that's a great question. So I think in the study empirically, we took a relatively non-parametric approach, right? So we basically threw all of the features that were available in that study into a model that then kind of made more data-driven choices about like how much complexity.
2, 10, 100.
So I think it ranges from like 10 to several hundred basically in these data sets.
I don't know a lot about how the risk modeling is done in these applications, but on the previous slide, you said that you have to care about people in different percentiles of risk and the number 7 in there. Why is that 7 not dependent on how the risk is modeled? Like if we were weighting that risk differently, wouldn't the 75th percentile like only have to be cared about as much as the 25th percentile? Or is there something like inherent about the way we measure risk where that 7 is important?
So I think the important thing is that you are trying to estimate the baseline outcome absent intervention and not the difference in outcomes. So I think you're correct that the specific number here could change depending, like there's probably just like multiple, like whatever choices, like I could have fit a random forest, I could have fit an XGBoost, I could have fit a legit regression, right? To all estimate that quantity and there would be some like variance between those. And that might change the exact
But you're saying there's no design choice here about how you rank the outcomes. Like even if your model is perfect, the scale that you're measuring risk on, that's like a given, that's not a design choice.
So I think the scale, yes, so basically we picked something that was basically like the primary outcome for each of the studies in question, right? So there's like a particular variable that's like, one intervention is trying to increase income, one is trying to improve labor force participation, whatever, right? So I think once you pick the outcome that you care about and then there's not really like a design choice after that, besides like.
And this seems to translate to whatever that outcome, the 75th, 25th percentile thing.
Yeah, so basically like, the reason I picked this number to summarize the result is that the majority of entries in the table basically across like all the different domains, which all have different outcome measures and all of that, are all bigger than that.
question about the figure on page 10. So, what if the two curves cross over? What is the implication of that? And if the estimation of the treatment effect is already taking into account of the 40%, sorry, 60% out of the 100, the data sample, basically, is there a correction for selection bias in the estimation of how the effect?
Yeah, these are great questions. So first, if the lines cross, the implication of that is that the sort of bias in the estimate of the treatment effect is so bad that you're losing ground compared to targeting only on risk score, basically. As to whether there's any correction, no, there's no correction. So this is just fitting basically an estimator for heterogeneous treatment effects on the data as if, we were assuming that it satisfied, kind of normal causal assumptions. So I think in principle, basically, the challenge is that in observational settings by itself, there's no way for me to correct for that bias, right? Because there's no way to identify what the bias is, basically. But if I had additional information that let me do that in a particular setting, then yeah, maybe I could do better at this end of the scale. If there's no other questions, I'll keep moving. All right, so the second piece of work that I'm going to talk about now is joint with my collaborator, Bryan Wilder, who's the chief data scientist at Allegheny County Department of Human Services. And so in this work, our motivation is in these kind of human service settings, limited resource allocation, again, prioritization rules. And here we're thinking about now the challenge, right? Like, why don't we have more randomized controlled trials, right? Like, why is it so hard to learn causal effects? So the problem is that running an RCT is perceived as being really costly for the quality of the services that you as an agency are offering right now, right? Because you already have some way of prioritizing people. The agency by definition believes in it. And from our previous slide, they're not like crazy to do that, right? There is some reason for thinking that, whatever risk score they're using right now could be a reasonable way of making decisions. And so if you just start randomizing people, then suddenly, right, you're giving interventions to people that you don't think that need them that much and denying assistance to people who do. And this is something that people just don't want to do, right, with operational programs that are serving lots of people who really need help right now. On the other hand, that seems to be a relatively poor, seems to have unfortunate consequences for us in the long run, right? Because it means that we're unable to actually improve the quality of the decisions that we're making because we're not gathering the data that would allow us to do that. And it means that even at a higher level, for example, it makes it really hard to think about program evaluation because if I don't collect data that's at all randomized, it's really hard for me to say even, is this program on average helping people, right? Much less like heterogeneous benefits or who is it helping, just is it doing something at all on average? And it turns out that in most applied settings of this forum, there is shockingly little good evidence about which programs are effective or not. And so it seems like there's really an enormous amount that we could do to improve the design of human services, for example, if we were able to get better evidence about kind of even that sort of simple question. So here we're going to introduce a little bit of a quantitative model. So we're going to think about a population of people that are characterized by covariates X, as well as potential outcomes Y0 and Y1. So Y0 is the outcome that someone would experience if they did not receive an intervention, and Y1 is the outcome that they would experience if they did receive the intervention. And so we're going to try to capture this dilemma between adhering to whatever kind of beliefs we have right now about an appropriate targeting strategy versus gathering more evidence for the future. And so the way that we're going to do that is by saying that the decision maker has a pre-specified targeting utility function. And this is just some function of the individual's covariates that says, based on whatever we know already, how much does the decision maker want to offer treatment to this person? So our framework is, for everything from now on, is basically agnostic as to how that's specified. But the running example that you could have in mind is where this is a risk score, right? So I've estimated using kind of historical data, the baseline outcomes, what would happen if someone is not offered treatment. And then I want to offer treatment to higher risk people. So this basically captures that I don't want to deviate too far from what the agency is doing in practice right now. So that's kind of a constraint that I want to adhere to, and then I also have a limited budget that I can offer treatment to at most a B fraction of the population. So the two things that we're going to try to balance here is, on the one hand, we want to offer treatment to people with large risk scores, and on the other hand, we want to learn causal effects. In this paper, we're going to formalize learning causal effects in kind of the simplest way possible, which is just to learn the average treatment effect. But I think there's a really kind of natural follow-up direction here that's about, optimal learning of heterogeneous effects. That's something we're kind of thinking about now. So the central tension, of course, here is that learning about treatment effects in the most strongly credible way would require randomization, and so there's a tension between these goals. So what we do in this work is we present kind of a framework to directly optimize that trade-off between targeting and learning. So we're going to get a Pareto frontier of different targeting strategies, and at one extreme is a standard RCT. At the other extreme is just ranking people by risk score and offering treatment to the highest risk people. But we're going to get kind of the spectrum of all the possible designs in between. And what we'll find is that empirically, these trade-offs are kind of a lot better than we might have thought. So we can get, basically most of both of these goals simultaneously without giving up too much of either one, as long as we're willing to compromise just a little bit. So before I talk too much more about the kind of the technical details here, I want to contrast the problem formulation that I just laid out with one that I'm sure is on a lot of your minds, which is online learning. So it would be very natural to model this setting as a contextual bandit, where individuals arrive online, I map their features to the treatment that they're assigned, and I want to, optimize some kind of cumulative regret. So there's kind of two classes of issues with this paradigm that led us not to pursue this, at least in the context of these application domains. So the first of these, which is a more fundamental issue, is that the contextual bandit framework is kind of set up around the idea that we have this one goal, which is long-term regret minimization. And it turns out that a lot of the things that you want causal estimates for are not really within that framework, right? So for example, you might want to learn which programs should I expand or cut, or use this information to inform other jurisdictions, right? There's a lot of reasons that you might want evidence to inform programmatic decisions that are not actually the individual level targeting decisions. And so, and honestly, I think that could be a lot more impactful in most cases, right? Than like deciding who exactly gets which resource. It might be deciding which programs we should offer at all that has the bigger impact. Another kind of thing that's a little bit difficult to fit into the box, though there's some attempts in the bandit literature, is that policymakers might want to guarantee some level of quality kind of in service provision across all time points, right? They don't want to incur kind of costly exploration phases. And then on top of that, there's a lot of operational issues, right? So for example, a lot of the outcomes that we deal with are 1-year outcomes, right? Whether something happens in a long period of time. And so that means that there's this now 1-year delay basically in the process of adapting via a contextual bandit. And so what we're going to propose instead are entirely non-adaptive designs that can be implemented just as a kind of a simple post-processing step on top of whatever risk model the county is already using. Any questions here before I start to go more into the technical portion? So our approach is going to be to try to write down an optimization problem, which will be over an allocation rule P. And so P is a function of the covariance X, and it maps any individual I to the probability with which I'm going to offer individual I an intervention. And so the actual decisions are going to be then randomized independently with that probability. So the question now is, what is the best function P given a particular set of preferences? And the way that we're going to formalize that is as an optimization problem, where the objective is to minimize the mean squared error with which I estimate the average treatment effect. So this means that basically I want to collect data in such a way that I will be able down the road when I get that data to estimate the treatment effect as accurately as possible. And so the way that I'm going to kind of operationalize that is via the asymptotic variance of the estimator of the treatment effect. Because we can decompose error into bias and variance. We can use unbiased estimators. So all of the error is due to the variance, and we'll try to minimize that basically over our choice of the data collection policy. The constraint then that I'm subject to is that I have to achieve at least a given level of expected sort of targeting utility with respect to this pre-specified function. And so in our running example, this might mean that I am constrained to offer treatment to at least some percentage of individuals that would otherwise experience an adverse outcome. So you can think of this, for example, as saying that if I measured my targeting rule as a kind of a predictive model for the bad outcome, it would mean that the recall of that model can't degrade too much, right? So basically I can't be like serving a model now that's that much worse than the one that I had before. So in terms of the way that we spell this out, so the objective function here to minimize the variance of the average treatment effect estimate, this is a convenient way to phrase the objective because we can now draw on very kind of like old well-established results in the semi-parametric statistics literature to write down actually a fairly neat closed form for what that is. So basically, the asymptotic variance of any estimator of the average treatment effect is lower bounded by this quantity. And under some relatively mild assumptions, we have efficient estimators that achieve exactly this bound. So basically, this is a pretty tight characterization of what is the error in estimation that's going to be supported by a given data collection policy. So this bound now has sort of a few moving parts. We'll notice that the part that we choose here is in the denominator, right? So this is the allocation probability for an individual with covariance X. And it appears in the denominator because if I make it close to 0 or 1, the variance blows up, right? So as the assignments get closer to deterministic, I suffer more and more error in my estimates. Now, there's a bunch of other terms here that I'm going to sort of hand wave away, basically. So there's this added term over here, which doesn't really matter because it doesn't interact with P, so it's irrelevant for the optimization. But then there's these terms in the numerator here, which are the conditional variance of each of the potential outcomes given the covariance. And so these are kind of tricky because they are effectively unknowable until we actually run the intervention, right? Like until I collect data, I don't actually have any way to know what those are. And so what we're going to do here is to suppose that the conditional variances are at least bounded. And so then we can see optimizing this simpler objective as minimizing an upper bound on what the variance of the estimator could be. And so we can see this basically as optimizing for the worst case variance structure, which is where the variance in each of the outcomes is equal. So there is kind of a recent line of work that tries to put together like adaptive trial designs that exploit cases where the variances are not equal. So this is the so-called name and allocation problem. And so there the idea is that if I knew that one of the arms of the trial had much higher variance than the other, I could improve the power of my estimates by allocating more samples to the arm with higher variance. And so basically what we're saying is because we're not looking at adaptive designs, we don't have any way basically to exploit that scenario if it does arrive. And so we're optimizing the kind of conservative case of equal variance. And so if we looked at this objective, what would happen if we optimized it without any constraints is that we would get P equals 0.5 for everybody, right? So we would just recover the kind of like standard randomized controlled trial where I would randomize people to treatment and control with equal probability. Of course, the motivation here is that we do have constraints. And so here's what the actual problem might look like, where I have this objective, but now I'm subject to a constraint that imposes a lower bound on the sort of utility that I have to accumulate with respect to this function U. And I also have to satisfy a budget constraint that I offer treatment to at most some fraction of individuals. So this framework is easily extensible. We can add other constraints as well. So in the paper, for example, we talk about fairness constraints across subgroups, where I might, for example, impose that the utility accumulated by different groups has to be comparable, or even that treatment is just offered at comparable rates to different demographic subgroups. So all of these are pretty easy to incorporate as long as they can be written as convex functions of the decision variable P, which is usually the case. So this is a problem that we would like to solve. Maybe I'll pause here, kind of questions about this formulation.
Maybe you're about to talk about this, but we don't know you, right?
So yeah, so we do know you. So you is you could look at this as like the existing risk model, for example.
Why is there the probabilities not at 0, 1 element again?
Yeah, so this is just because the objective is undefined at P being 0 or 1. Now, we know that the optimal solutions wouldn't lie there because it would also make the variance infinite. But sort of just to keep things a little bit easier technically, we just impose the probabilities are clipped away from the extremes. So you can think of gamma as just being some like very small constant here.
At some point that the objective or something that looked like the objective was a lower bound on the thing that you actually cared about? Or was that, am I misremembering that?
Yeah, well, so I guess there's two steps happening here. So this is an upper bound on the efficiency bound, which is itself a lower bound. But it's basically a tight lower bound, right? Like we know estimators that achieve the efficiency bound. And so this is an upper bound on that.
Okay, so you're not necessarily minimizing an upper bound on the thing that you care about, but it's close to that.
Yeah, it's minimizing an upper bound on what we care about subject to more assumptions, right? So for example, like we know estimators that achieve the efficiency bound if you impose, for example, like assumptions on being able to learn outcome and propensities at like at least n to the 1/4 rates, or like there's kind of additional technical conditions that you need to impose to ensure that efficient estimators exist. But when they do, this is an upper bound on exactly the quantity that we would care about.
Got it.
Okay, so then I'll kind of walk through how we go about solving this problem. The kind of essential difficulty is that it's a optimization problem over a function p here, right? It's not like there's a sort of a finite number of decision variables here. We're really optimizing over a policy. And so normally, kind of from a computational standpoint, this is where I would start talking about like the class of policies that we're going to optimize over, right? I would say, so now we're going to optimize over linear policies or policies parameterized by neural networks or decision trees or whatever else, right? And then we would have results that somehow depend on the complexity of that class of policies. So that's kind of like the standard thing that we would do from like a policy optimization standpoint. It turns out that we do not need to do that here. So there's actually kind of a sort of nicer, cleaner way of characterizing exactly what the optimal class of policies looks like. So in particular, the intuition here is that the objective function is fully separable over the covariance x, right? Because the objective function is this expectation, which is separable. So the only thing that is coupling together the decisions that I make about different individuals are the constraints themselves. And so that motivates us to look at the dual problem, where I introduced the Lagrangian here, which includes the objective function, but then also replaces the constraints. And so I'm going to represent all the constraints just sort of generically by these functions g here. So it replaces the constraints, instead of having hard constraints, having soft penalties for violations of the constraints. And so the amount that I violate constraint j by is penalized by some scalar lambda j, which is the dual variable for that constraint. And so now, because this problem is convex, the original primal problem is equivalent to this dual problem, where I have the outer optimization that's over the dual parameters here. And so the reason that this is really nice computationally is because once I write things out in this form, it sort of reveals that once I know the value of the dual parameters, the decisions actually do become fully separable over individuals, right? Because I've sort of fixed this, like the shadow price, right, on each of the constraints. And so with that in hand, now I can make a per individual decision of how much I want to trade off the variance that they contribute to my estimates versus the amount that I have to kind of like charge them for violating the constraints. And so once I know the dual parameters, formally it means that I can move the minimization inside the expectation here, right? I can do this minimization separately for every individual or every set of covariance x. And so this means, so this suggests kind of the following algorithm, where I use a sample from the covariate distribution to estimate the optimal value of the dual parameters. And so the way that I do that is that given this set of now n data points, I can write down kind of the sample average approximation to this problem, right? So I can write down an optimization problem where I now have only n decision variables, which correspond to the allocation probabilities for each of those n individuals. And so that gives me a now finite dimensional convex optimization problem. I chuck it into my favorite solver and I get an answer. And then I throw away the primal solution, right? I don't actually care about the allocation probabilities for those individuals in the training set. All I care is that from the solution, I can then extract the optimal value of the dual parameters in that sample problem. And so, so I use that training set then just to get the sample optimal duals. And from there, I can now make separate decisions for every individual as they arrive at test time. So when I want to make decisions about an individual, then I just, as people show up, as they arrive, I then solve a separate, now one-dimensional convex optimization problem for them. So I plug in the lambda hats that I got from the sample problem, and I find their kind of, personal optimized allocation probability just by solving this, which is now a, very simple problem to solve. So, questions so far about the approach here?
Is there possibility that the constraints that were not in the original problem, so like group fairness would introduce non-convexity into this problem?
So at least the formulations that we study in the paper, things like similar levels of utility across groups, do fit into this formulation. So there are additional constraints that are linear in P basically, so we can fold them in fairly naturally.
Does it give you any insight into the set of X? So how many X's you need, or what the quality of the prediction that they give you?
Yeah, so I'm gonna talk about that in a couple slides here.
Can you quickly talk about how this formulation will guarantee the resource limit when testing time, during the testing time?
Yeah, so basically the intuition is that if we got so there will be a lambda associated with the resource constraint, right? And if we got the value of that lambda kind of correct, it will basically penalize, including, basically there will be some penalty here that's like lambda times P. So if I make P bigger for an individual, it's penalized by some amount. And that value will be set precisely such that when it's balanced against the variance term, I end up satisfying the resource constraint. So to give a little bit of intuition first about what these policies look like. So in the case where I only have the utility and the budget constraints, so no fairness constraints or anything like that, I can just graph the policies here because each individual's allocation probability is a function of their risk score U. And so intuitively, as we expect, people with higher levels of risk get assigned bigger treatment probabilities. And the policies tend to look like kind of S-shaped curves somewhere around this cutoff, which is in this case, I think the simulation is where I had budget to treat 30% of the population. So this is the 70th quantile or percentile, sorry, of the risk distribution. So if I was treating purely the people at highest risk, I would treat everyone above this cutoff and no one below it. And the policies that we get basically redistribute some probability mass from people who are, just above the threshold to now being able to treat people with some probability, at least out into the scale, with kind of the sharpness of that function controlled by the amount of utility that I depended. So the policy likely gets a little bit less easy to visualize if I have more constraints, but this is at least what's happening in this kind of simple case. And this is the kind of intuition for why this is like a pretty easy post-processing step on top of whatever kind of your local government is running in practice right now. So this approach has a few nice properties. One is that allows us to make separate decisions for every individual, right? I never now need, at inference time, I don't need to solve sort of a joint optimization problem over everyone. I just can make decisions for people as they arrive. Second, it's really computationally easy. I just have to solve this convex optimization problem. And then finally, we're going to be able to give fairly strong sample complexity guarantees. So here's the kind of somewhat simplified statement of the result here. So basically, to learn a policy that is optimal with respect to the objective function minimizing variance and feasible, right? So all the constraints are respected, all up to some additive loss of epsilon, right? So the amount that we might violate the budget constraint by, or the amount to which we've suffered excess variance. I need a number of samples that scales like 1 over epsilon squared. And then something about how close the probabilities get to 0 or 1, basically. So estimating the dual variables gets harder as the probabilities get more extreme. So this is, I think, in some sense, the best that we could hope for, right? So like we never had to have something like a VC dimension or some assumption about like the optimal policy lying in a particular class. Really, we showed that the optimal policy was parameterized just by the dual variables themselves. And there's only a few of those, right? There's like 2 dual variables in the example that I showed you, maybe a few more if you add fairness constraints. But really it means that you're learning something like on the order of like 5 parameters. And so you don't need a lot of samples to do that, right? It's not that many things to learn. Kind of, if you're interested in a little bit more detail, there's more of this in the paper. Basically, this sort of like the scaling with gamma here is really coming from you needing an upper bound on how large the dual variables could be in magnitude, because that controls something about the sharpness of like the trade-off between the objective and the constraints and how precisely you have to quantify everything to get them all right, sort of simultaneously. So that's a measure of kind of like sensitivity of the distribution to sort of errors in estimation. And this is kind of a specific, instantiation of that now. But if you added more constraints, it would be something about like, whether the constraint structure is kind of well conditioned, basically. So, any questions about this? Okay, so then I'll show a few empirical results where we try to empirically assess this trade-off in a real-world human service setting using data from our partners at Allegheny County. So we look at a couple of empirical settings in the paper. I'm just going to show results from the first of these in the talk, which is data on the outcomes of formerly incarcerated people who are re-entering the community. And so we use administrative data from the county to predict the baseline risk of this outcome, in this case, re-entry to jail in the next year. And we simulate a hypothetical new intervention where basically individuals' outcomes improve with some probability. So our goal is to evaluate sort of these 2 competing goals. On the one hand, the fraction of people who would re-enter jail in the next year who we offer this intervention to. So that's our measure of kind of immediate quality of service. And then we want to compare that to the variance of the estimator. Now, because I don't think it means anything if I just tell you like the variance was 10 or whatever, right? I'm gonna instead present variance in terms of basically a power analysis. So I'll show you the sample size that you would need in order to detect the true average treatment effect in the simulation with a given level of type 1 and type 2 error. The comparison point that I'm going to show here is a regression discontinuity design. So this is maybe the kind of go-to strategy in this setting in practice, where you might notice, because I'm basically thresholding a kind of well-defined risk score to make a decision, I could compare individuals who are on either side of the threshold, basically, and see if there's an improvement of outcomes right around that discontinuity. So this is formally known as a regression discontinuity. It's not estimating quite the same effect. It's estimating an effect that's local around the threshold, not on average over the population. So it's not quite apples and oranges, but I'm still going to include it as a reference point because it's probably the most salient kind of practical alternative. So here's the one plot that I'm going to show. So this is exactly the Pareto curve between the sample size needed to estimate the ATE and the fraction of individuals who re-enter jail in the next year who would be offered treatment by this policy. And so the blue curve is the Pareto frontier output by our method, where every point on that curve is a different policy. And I've highlighted a few particular points here. So one is where we impose no usability constraint, we recover the standard randomized controlled trial. There we would need something like 3,000 samples. The next is if I demand about 90% of the kind of immediate targeting performance as the status quo. And so here I need something like 5,000 samples in order to move the utility up that far. And then finally, the regression discontinuity, which is where I deploy the status quo policy, right? I just target based on risk scores deterministically. I get that last 10% of targeting performance, but it inflates the sample size requirement to over 20,000. And so this is really kind of consequential, especially in like a local government context where, this would mean waiting, several years at least to, gather any sort of meaningful evidence about this program, which is probably not a super policy relevant timetable compared to getting results within, a year or less, which is a little bit more feasible. So we see similar results. This is, one particular setting of, the synthetic treatment effect and the budget and so on. The results are, very qualitatively similar. in terms of the general sort of inflation and sample size that would be needed to run a regression discontinuity or to achieve 90% of the kind of the optimal targeting performance with our method. So, so this is very much, in the, sort of we have a paper out about this framework, but the sort of the overall project is very much in progress. We're working now with ACDHS to implement these methods, focusing right now on targeting a new cognitive behavioral therapy intervention, trying to balance this trade-off basically between offering it to people who are most likely to need it now versus gathering the evidence that will inform whether these programs should be scaled in the future. So to kind of wrap up here, I think, part of, my conclusion from this work is that, while there are sort of these real trade-offs in social interventions, right, between targeting now and learning for later, we do have the opportunity to mitigate those trade-offs by being more particular basically about what we ask out of algorithms. And so broadly, I think as computer scientists, it's easy for us to kind of over-index on, for example, just like making the predictive performance of the model better, right? And like eking out a little bit more AUC. But that is unlikely to be what actually moves the needle in these domains. And so if we sort of go back and sort of bake in more of the objectives that we want into the process, there's really the opportunity to balance these sort of competing desiderata in a way that really works out kind of at least reasonably with respect to all of them individually. And so in the longer run, our hope is that this will improve the quality of services by reducing the cost of gathering evidence, right? That we'll be able to do more widespread and high quality program evaluation, and that will ultimately help us build better social services. So thanks everyone for being here, and I'm happy to answer any questions.